Welcome to the VIS 2014 short paper session on tests and multimedia. I'm Minlu from Shenzhen University, China. And today in this section, we will have 8 wonderful words. And now let's welcome our first speaker, Mona Alebri. She will present her nice work on the design patterns in right to left visualizations, the case of Arabic content. Okay, so Muna, now you can share your screen.
Okay, thank you. Can you see my slides without the notes?
Yes, it is.
Okay.
Yes.
Great.
Yeah.
Okay, thank you. Hi, everyone. I'm very excited to be here and present a project that is I personally very passionate about. In this work, we map the design space of visualizations found in right-to-left scripts, and we take Arabic as a use case. My name is Noëlle Alebri. I recently finished my PhD from UCL and currently affiliated with the UAE University. And this work was in collaboration with my co-authors, Noëlle, Rakotondravony, and Lane Harrison. So the rise of data availability, digital media, and data journalism has expanded the audience of data visualizations to a more diverse population, necessitating inclusive research direction, and languages and scripts are an important aspect in diversity and inclusion. Right-to-left script users such as Arabic, Hebrew, and Persian constitute over 1 billion potential users, posing new design requirements that may challenge existing approaches that predominantly focus on users from Western and economically developed worlds. Directionality's importance in influencing spatial perception, temporal representation, and preference and expectations has been demonstrated in HCI research, cognitive science, and user interface research. Direction is embedded in visualizations that represent data with trends, ordered sequences, or time series data. And the mapping of right to left visualizations and their elements is a less explored area. Therefore, we raise the following research question. What design patterns exist for data visualizations found in Arabic scripts? And we focus on the elements of the visualizations, their presence, their absence, and the direction as well. And we don't present best practices, but rather common practices, which may be very helpful for those who are unfamiliar with right-to-left scripts. To understand the design space of right-to-left visualizations, we focus on Arabic as a use case and particularly news visualizations, as these are widely consumed by the general public. From 7 popular news outlets, we selected 51 data-driven articles that contained at least one standalone data visualization. This process resulted in 128 visualizations covering a wide range of topics. Next, 2 authors coded the visualizations independently, considering position, presence, and absence of the following categories. The first was the chart category, where we looked at, for instance, the x-axis direction, y-axis position, and the chart type. The second was the text category, which included elements such as presence of title, caption, and annotations. And the final category was the source, where we looked at the source position, data availability, and ownership of the visualization. One of the key findings from our content analysis was regarding the axis direction and position, which was done on charts such as line chart, bar charts, and scatter plots. We found 2 distinct patterns based on the data type. The first was in terms of when the x-axis was depicting numerical data. We found that 58% positioned the y-axis on the left, as you can see here, and the x-axis direction was from left to right. On the other hand, the less common pattern was where 33% of the visualizations positioned the y-axis on the right and the x-axis was from right to left. However, we found that this pattern was within visualizations that came from independent news outlets in comparison to mainstream media. Regarding the categorical data, where direction of the x-axis doesn't really matter, we found that there is a considerable agreement of design, where we found 81% of the visualizations position the y-axis on the right. We also found that 12% of the visualizations were borrowed or replicated from an English or French version. Among these visualizations, there were two popular adjustments. The first was the literal textual translation from English or French to Arabic, or a textual translation with the design mirroring. We observed that the second pattern was more frequent in our sample, where over 66% of the sample mirrored at least one chart component. Please look at our paper for more common design practices and right-to-left visualizations regarding the logo position, the source, and the legend. In conclusion, our analysis of design patterns and right-to-left visualizations revealed that designers tend to favor right-to-left approaches for categorical data, while in contrast, a mix of right-to-left and left-to-right approaches were observed with numerical data. Suggesting that there is some level of ambiguity in the design decision process. This might be because some designers might be inspired by web design guidelines for right-to-left scripts to mirror the x-axis, whereas others who are using the left-to-right approach might have applied coordinate system directions, as they are similar in English and Arabic. Therefore, we need more clearance regarding the guidelines are used. Therefore, future work should interview designers to understand their assumptions, their references, and the guidelines that they use. There is also a tacit knowledge to use mirroring, suggesting that designers might benefit and actually use mirroring features and visualization authoring tools. In the end, I hope that our research encourages researchers to consider direction and motivate more inclusive approaches in our visualization design practices. Thank you, and I'm happy to receive any questions.
Hi, thank you. Thank you, Mona, for your wonderful talk. Here is a very quick question. In this work, you study how the right to left or left to right design on visualization. Are you considering study how the task, say, how to identify the trend can be influenced by the right to left or left to right layout?
The task? You said the task.
Task of like identifying trending in a chart. It may be, yeah.
In our study, we only looked at the design pattern, so it was a content analysis. We hope we're in the process of running an empirical investigation where we ask participants to run tasks. And this is led by my co-author, but we haven't really looked into tasks in this study, but it's definitely something that would help us reach more of a clear guidelines.
Okay, great. Thank you, Muna. Thank you for your talk. So now let's move to our second talk, which is from Dennis Bromley. He will give a talk on Dash, a biomodal data exploration tool for interactive tests and visualizations. Yes, Danny, nice.
All right, thank you. Can you see my slides?
Yes.
Brilliant. Okay, so hi, my name is Denny Bromley. Together with Vidya Setlur, I work at Tableau Research. And today I'll be talking about Dash, which is a tool to help people see and understand their data in a bit more intuitive way. So let's see. There we go. So these are the top data-related hashtags per Bing Copilot about a month ago, and they're all super impressive, right? But so talking about text in the face of these technologies feels a little bit like bringing a pencil to a GPU fight. But if we look at every newspaper and magazine and journal in the world, right, institutions whose sole purpose is to disseminate information and data, we can see that they're all text first. In fact, even data-driven articles backed by concrete scientific data are still text first. So the question is, what are we missing, right? We're in a $50 billion industry to help people see and understand their data, and yet we backseat people's demonstrably preferred information channel. So we can begin thinking about this by looking at Lundgaard's paper about natural descriptions of data charts. So in it, they create a semantic hierarchy where the lower levels describe the structure of the chart, the middle levels describe what the data looks like, and the top level puts it all into context. It brings in domain knowledge and helps you understand what the data is telling you. Lundgaard also showed that the natural language narratives use all four of these levels together, right? So here the text is color coded from the original paper. And so we were inspired by this, and we made a modified version of this hierarchy that describes the four levels of data consumption. The lower levels describe the raw data. The middle levels represent statistics and relationships among those statistics. So you can think correlations and trends and outliers. And the top level represents high level understanding, the integration of domain knowledge and an interpretation of what the data relationships actually mean. And again, you can see that a natural language description of data moves among these levels in a very natural and comfortable way. So if you look, you can see that the lower levels can be described very well by charts, and the upper levels can be described very well by natural language. And then there's this nice smooth trade-off right in the middle. So given this, one of our takeaways is that the lower levels are where you can see your data, but the upper levels are really where you understand your data. And so we wanted to make a tool that could merge these levels in a smooth way to help people both see and understand their data in a continuous, easy to use way. So for that, we built Dash. As you'll see in the video that I'm about to show you, Dash moves between high-level text and lower-level charts and data to create an overall data presentation that helps people pull some useful meaning out of their data. So with that, hi, thank you for taking a look at our work. Today, we would like to talk to you about Dash, a data analysis tool that moves smoothly between text and charts, crafting a data exploration narrative that navigates between low-level data and high-level analysis. Let's say we've got some Seattle housing data, and we want to find a good neighborhood for a family of 4. There's so many neighborhoods and factors to consider that we just don't know where to begin. This is where Dash can help us. We tell Dash what we're looking for, and it immediately offers us an overview of several neighborhoods, focusing on factors like bedrooms, bathrooms, house size, and price that would be important for a family of 4. Reading this initial paragraph, it looks like zip code 98178 is a good bet, so let's ask Dash to expand on that neighborhood. 98178 looks pretty good, but Seattle's a big city. Let's take a bird's eye view of all the neighborhoods, paying special attention to house size and lot size so our family has plenty of room to run around. This is a super handy chart. Wow, okay, so this zip code has huge lots. Tell me more about 98121. All right, so the lots are large, but the houses are actually pretty small. Let's take a look at the price. Okay, it's not too bad relative to the rest of the city. But wow, 98112 is really expensive, even for Seattle. Let's see what we're buying for that. Okay, I see. That neighborhood has some really big houses. But hey, we're still window shopping, right? Tell me more about 98112. Yep, big, beautiful houses, but yeah, pretty expensive. Looks like we should take the family and go have a look at 98178. As you can see, we're pretty excited about Dash because it helps data explorers intuitively move between text and charts, creating a simple yet precise data exploration experience. People love charts and graphs, and for a good reason. But there's also a reason why newspapers, magazines, blogs, and journals are all text-first publications. The goal of Dash is to give people the best of both worlds. Thank you for taking the time to listen. We hope you enjoy the paper. Okay. Hi. No, there we go. Okay, so that's the basic Dash user interface where you can sort of smoothly drag data back and forth between text and charts. So this is the Dash user interface here, and on the left you can see multiple paragraphs, which are the block level unit of text. Within that paragraph, however, is a tree structure of sentences and sentence fragments, breaking down the paragraph into smaller and smaller pieces. The individual pieces hold metadata, including semantic level and the fields and the data values that they refer to. So for example, the phrase higher than average price might be linked to the price field and a value of $1 million. So under the hood, the text is hard linked to specific data fields and values. When you drag a word or words from the text area, we create a small JSON packet that carries the level, field, and value metadata. If you drop this on a chart, the chart has a few ways to interpret it, depending on the current chart context. It can change the chart type by adding a new dimension, it can add a label, it can add a reference line, anything like that. So for this prototype, we only used a handful of chart updates, but in principle, you could do anything you wanted to. Similarly, if you drag the word to show me more at the bottom, Dash generates a wholly new chart. The JSON text packet is sort of the Dash-wide currency of exchange. So when you drag a mark from a chart, Dash generates the same packet, updated for that mark's data field and value. When you drag a chart mark or word, anything that can generate that JSON packet, to tell me more at the bottom of the interface, we ask the LLM to generate some descriptive text. If the drag metadata is level 1 or level 2, we generate level 3 or level 4 text. And if the drag metadata is level 3 or level 4, we generate level 1 or level 2 text. This is to emulate that flowing narrative style that was described by Lundgaard, where the narrative moves among the different semantic levels. So for evaluation, we interviewed 12 people of varying degrees of technical sophistication and asked them to use Dash to find a good Seattle neighborhood for a family of 4. Overall, people liked it and thought that the back and forth mixture of text and charts was useful. However, the lines between semantic levels were sometimes not as clear as some participants would have liked, and the relatively simple data set left some people feeling like they wished they could dig a little bit deeper. With that said, the primary purpose of this research probe was to evaluate the back and forth interaction between text and viz, and that seemed to, and obviously there are details. So with that, I'd like to say thank you. We'd happy to take any questions. And an unabashed plug, Tableau Research has internship openings for next summer. So if you're interested, please come by and talk to us, or we're virtual, so drop us a line. So thank you.
Thank you, Danny. So I think your discussion observations on the tests and the visualization, how those two play in the result explanation is quite insightful. And I'm quite interested in the interface that you developed to explore the biomodal. Do you think it's possible that we need some new interactive interface to interplay those two different modules more closely? I mean, like break those paragraphs into sentences, then integrate into visualization, something like that.
Yeah, so I mean, I think as we were going into this, it became more and more, as we dug deeper, it became more and more obvious that much of what people take away from things is with text. But as was showed by Lundgaard, right, the different semantic levels are present within any given piece of text, like a paragraph. And so, like in this particular example, Dash goes all the way down to the word level, but it's a hierarchy, so it also has semantic levels at kind of phrase and sentences and all the way up, so you can talk about the different semantic levels at each piece. I'm not sure if that exactly answered your question, but that enables you to move back and forth in that manner.
Yeah.
I'm not sure if that answered your question, though.
Yeah, it is. Thank you, Danny. Thank you for the talk. And now we move to the third talk, which is from Hannah Kober, and she will present the work. And now let's welcome Hannah. Hannah, are you here?
Yes, I am.
Yeah, you can share your screen now.
All right, perfect.
Yes.
All right, let me just share that. And all right, can you see the presentation now?
Yes.
Okay, perfect. Hello, I am Hannah Bako. I'm a PhD candidate at the University of Maryland. And today I'll be presenting my paper on evaluating the semantic profiling abilities of LLMs for natural language utterances in data visualization. So natural language has become a popular interaction paradigm for data visualization generation, as it's easier for users to articulate their visualization intents through natural language than using programming constructs. In recent years, large language models have also been employed to power natural language interfaces for data visualization generation. However, enabling LLMs to understand user intent for visualization is complex. And the challenge here lies in accurately interpreting the user's language to identify key elements such as data attributes, transformations, and visual tasks, which we refer to in this paper as the semantic profile of an utterance. Now, we know that human language often contains uncertainties, which are like ambiguities or underspecifications that make this process challenging for LLMs. So, for example, in this user's question, the LLM must address two levels of uncertainty in the use of the synonym family and the ambiguous term physiological traits. So, proper resolution of uncertainty is essential for generating the correct semantic profile. And so, in this work, we investigate how well current LLMs perform at semantically profiling natural language utterances for data visualization generation. And our analysis on LLM's semantic profiling capabilities covers three key dimensions. First is clarity analysis, which involves uncertainty identification and resolution. And this, we identify three types of uncertainties. First is if an utterance is ambiguous, underspecified, or includes references to data that is missing from the input data set. Second, we look at the data context. And this captures the reference data columns and the data transformations that would need to be performed on the data set to transform it into a format that can be used to answer the user's utterance. And then finally, the semantic profile captures the visual task that's being described in the utterance. And this covers tasks such as filter, summarize, compare, trend, etc. And we classify visual tasks according to the taxonomies presented by Amar et al. And Munsna. And so to establish the ground truths in our evaluation, we collected a total of 500 utterances, which cut across 37 unique data sets. For the sake of time, I won't go into the collation process, but please see our paper for more details on this. Three of the authors of the paper then manually annotated all 500 utterances across the three dimensions of the semantic profile to generate the ground truth that was used for this evaluation. We also prompted 4 LLMs for annotations, 2 of which were proprietary LLMs, GPT-4 Turbo and Gemini. We also evaluated Llama 3 and Mixtral, which are open source LLMs. And all these LLMs had training data cutoffs in late or early 2003. For the sake of time, again, please see the paper for more details on how we prompted all these LLMs. So for our analysis, we primarily compared the annotations that were returned by LLMs to those made by the human annotators. The only exception to this was the data transformations, where we executed the Python code snippets produced by human annotators and LLMs, and then compared the schemas of the resulting transformed data tables. And now I'll go into our findings. So first, for clarity analysis, we found that the LLMs actually identified more uncertainties than humans. So while only 96 uncertain utterances were found by humans, LLMs on average found about 203 uncertain utterances in the entire corpus of 500 utterances. And only 25% of these uncertainties that were identified by LLMs overlapped with humans. And this indicates that LLMs are potentially hypersensitive to uncertainties in utterances. And we found that the LLMs would often describe uncertainty on how to perform analysis or missing context for data column values. So for instance, one of the utterances on the World Happiness Report dataset asks, can we conclude that higher happiness comes from higher freedom? GPT responded here that the query does not specify if the analysis should consider other factors that might influence happiness, or if it should be isolated to just happiness and freedom. To our human annotators, this was simply just looking at the correlation between the happiness score and the freedom. And so this opens up new interesting questions to explore, such as looking at if humans and LLMs identify and resolve uncertainties at different levels of abstraction. Also, can we leverage this hypersensitivity to help analysts think more deeply about their analysis process? Now, in terms of the data context, we see a total agreement between LLMs and human annotations for data attributes in about 57% of utterances, and 48% matches in schema for transformed data tables that were produced by the LLMs and human annotators. And overall, LLMs performed reasonably at identifying the right data context. However, of course, improvements are needed to optimize code generation for visualization context, which I think has been a longstanding challenge. In regards to the identification of visual tasks, we found a high level of disagreement between the tasks identified by LLMs and the humans. We found over 50% total disagreement and about 16% partial agreement in the annotations made by humans and the LLMs. And when we examined some of the cases with total disagreement, we observed that some of the issues were conflicting interpretations, such as the one seen here. So in this question on the Atlantic storms dataset, the user is asking what is the main factor on storms depending on the different status. Gemini returned correlation, while the human annotation was dependency, as correlation can't be calculated between a categorical and numerical attribute. Sometimes we also saw LLMs mix data transformations with visual tasks, such as in this utterance for the movies dataset, where mixtural returned aggregation, categorization, and relationship. And so overall, LLMs struggle with identifying the relevant visual tasks, and we need to explore how to optimize them for visual task inference. And so, in summary, we sought to evaluate the semantic profiling capabilities of LLMs. We evaluated 4 publicly available LLMs across 500 utterances and 37 datasets. We found that LLMs are highly sensitive to uncertainties in utterances. They perform reasonably at identifying the relevant data attributes and transformations, but they struggle with correctly inferring visualization tasks. I'd like to say a big thank you to all my collaborators on this work. I'm also on the academic job market this year, so please scan this QR code if you would like to learn more about my work and contact me. And now I'm ready for questions.
Thank you, Hannah. So we have a time for quick question. So as you identify your paper, the uncertainty or disagreement between human and AI is quite high. So what do you see we can do in the future to optimize LLM for visualizations?
So I think, sorry, could you repeat the question? I'm not sure if you were talking about the visual tasks.
I mean, how can we optimize the LLM to reduce the uncertainty?
That's great. I think there are kind of a bunch of things, right? So because the uncertainty is coming from the way that humans are phrasing the questions, right? So of course we could do things like trying to, identify. I think for me, the way I look at it is less on reducing uncertainty, but like trying to figure out why they are interpreting it as uncertain, right? And how we can use that to kind of guide the users in terms of either improving the questions that they're asking to make them clearer, or trying to prompt them to do, I guess, think more about what exactly it is that they're doing. In my opinion, I don't really see it as because like I said, like the example that I gave, it's more or less kind of like what exactly is the user asking, and then trying to figure out how we can lead them towards better analysis for what they're doing. I don't know if that answered your question.
Yeah, thank you, Hannah. Very timely research topic. Okay, so now let's move to our fourth talk, which is from Jen Hoffswell. So I will share the screen. Hannah, maybe you quit the screen sharing so I can share the screen. Yes, thank you.
Hello, everyone. My name is Jane Hoffswell, and I'm a research scientist from Adobe Research. I'm excited to be here today to share some of our work on representing charts as text for language models. This work was done in collaboration with several of my colleagues at Adobe, Victor, Eunyee, and Shunan. Given the rise of large language models and natural... Hello? Hello, everyone. My name is Jane Hoffswell, and I'm a research scientist from Adobe Research. I'm excited to be here today to share some of our work on representing charts as text for language models. This work was done in collaboration with several of my colleagues at Adobe, Victor, Eunyee, and Shunan. Given the rise of large language models, a natural question is how effective are they for chart question answering? Take this bar chart, for example. It shows population numbers for different age groups in California, Florida, and Washington. When viewing this chart, we might want to ask a question like, which state has the most young adults? We then hopefully get the right answer, California. Another type of question we might want to ask a language model is, well, how do you know that's the right answer? And it could tell us it has the largest pink bar. But how do we actually train language models to complete these types of tasks? One concern we had is that it could be hard for language models to robustly learn to perform chart-grounded Q&A from the pixel values of an image alone. Instead, what if we inject additional knowledge into the language model with a text representation like this, which provides additional information about the encoding, such as the mapping from age groups to colors? Our main research question is thus, are text representations useful for fine-tuning language models? We break this into three smaller research questions that are the main focus for this paper. How well do text-only models perform on chart-grounded Q&A tasks? How robust are these models to natural language variation? And finally, how helpful are text representations compared to images? Let's start with the first question. How well do text-only models perform on chart-grounded Q&A tasks? We consider two different tasks, question answering and visual explanation generation. Q&A tasks are more data-driven, like the question we saw before, which state has the most young adults? Visual explanation generation, on the other hand, relies on details of the visualization encodings to answer questions like, well, how do you know? With an answer, it has the largest pink bar. We then trained two models, T5 large and a much larger model, GPT-3 Curie. After training these models, we evaluated the accuracy on a held-out test dataset for both QA and visual explanation generation. Our main finding here is that while the accuracy is near perfect, around 99% for even our small model T5 large on visual explanation generation, there is a large gap in the behavior for general QA with accuracies of around 57 or 67% for T5 large and GPT-3 Curie respectively. Let's now move on to our second question. How robust are these models to natural language variation? In the previous experiment, we trained on template-generated questions like, for which state is the value for population the highest when age is 20 to 29 years? This question sounds much more formal than the questions we've seen so far, so to understand the impact of such natural language variation in the questions, we manually paraphrased the template-generated test set to sound more natural and tested our previously trained model on this new test set. We also ran some tests with automatically paraphrased questions using GPT-3 Da Vinci. But in the interest of time, I'll refer you to the paper for more detail on these results. The main takeaway I want to leave you with is that language models do remain mostly robust to natural language variation, and we can recover some accuracy through additional fine-tuning using automatically paraphrased data in the training dataset. Again, please take a look at the paper if you want to know more about this part of the work. Finally, we get to our last research question. How helpful are text representations compared to images? Here we have the initial data from research question 1, but we'll now focus on visual explanation generation as this task is more directly related to interpreting the visual encodings in the chart image. We compare this result to two image-based models, GPT-4V and Pixdestruct. And while our small text-based model, T5 large, had around 99% accuracy, we see that this can notably outperform the image-based models, GPT-4V, which was around 63% accuracy, and Pixdestruct, which had around 12%. With that, we've covered our main research questions for this talk. But since I have a little bit more time, I want to throw in a bonus question. What types of errors arise for current image-based models? To reiterate the results of our third finding, we saw a large performance gap between image-based GPT-4V and our small text-based T5 large model. As a reminder, we're focusing only on the visual explanation questions for this analysis. We then compare the ground truth color that is expected in the response to the result of GPT-4's completion for the task. Along the diagonal of this confusion matrix, we can see the number of cases where the ground truth and completion match. We do know that the ground truth training data was unbalanced across the colors, hence some of the drastically different numbers here in terms of correctness. We also see that GPT-4V never correctly selects cyan as the color despite it appearing in the training data. Instead, for the cases where the correct answer is cyan, GPT-4V most often selects green as the answer, though we do see some other colors selected for the completion in the rest of the data. In general, we also saw a larger number of off by one type errors, where the GPT-4V completion is a step off of this center correct diagonal line. Finally, we also see a subset of errors where the completion selected either blue or orange for the result, regardless of the ground truth. Again, it's possible such a trend is related to the unbalanced data in the ground truth training set, which blue and orange were the most common colors that we saw. Just for completeness, here's the final confusion matrix. Our final finding is that even GPT-4V can make systematic mistakes when using chart images only. We also saw some interesting trends in the types of errors, which would be interesting to explore more deeply in future work. That brings us to just about the end of this talk. In conclusion, we tested our fine-tuning method on two chart-grounded Q&A tasks and compared to image-based models. We ultimately found that we can get near perfect accuracy using a small text-based model for visual explanation generation, and that our models remain mostly robust to natural language variation. We also see that these models can outperform image-only models like GPT-4V, which does produce some systematic errors in the completion results. And with that, thank you all for your time, and a special thank you to the VIS organizers for all the work that went into making this event happen. I'm now happy to take any questions.
Thank you, Jenny. And here we have a question. So which model do you recommend if we want to do fine-tuning for this task?
Yeah, I think this is a tricky question. I think what we were seeing is that the text-based models were pretty good for this type of task and certainly require additional analysis. I think the image-only based models, as we kind of said, is a little bit tricky, especially for these visual explanation generation tasks where it does need to understand details of the encoding in order to provide an accurate explanation of what's going on.
Okay, thank you, Jen. Okay, so we move to the fifth talk, which is from Sunwoo. I will share my screen.
Hello, my name is Sunwoo, a recent graduate from Dr. Utley's Vibe Lab at WashU, and today I'm happy to present our work, Confides, a visual analytics solution for automated speech recognition, analysis, and exploration. The amount of audio data grows exponentially with each passing hour, and turning raw audio data into actionable intelligence can be complex, even with machine assistance, as it relies heavily on the accuracy of the algorithms and the quality of the original audio files. Therefore, the analysis of audio data remains fraught with inaccuracies and is notably time-consuming. Our work is further motivated by our collaborators for the Laboratory of Analytic Science. Their intelligence analysts required solutions that enabled them to efficiently and accurately explore audio transcription data. On the screen is a tool that our collaborators had developed in order to analyze transcriptions. Through our initial conversations at the beginning of this collaboration, they expressed that the tool looked cluttered, it was overwhelming to look at the transcription, and it was also very hard to follow along. Most importantly, they expressed that there was no communication of uncertainty. The lack of transparency within this tool has hindered the complete integration and effective utilization of speech-to-text technology within their workflows and analytical processes. To address this challenge, we aim to develop a visual analytics system that enhances the understanding of speech-to-text results by providing visual representations of the data and also highlight how confident the model is in its transcription. This tool was developed based on several iterative designs and bi-weekly feedback from our collaborators, which we held from January 2023 to December 2023. Our tasks and design goals for our system were derived from an initial 1-hour semi-structured interview with a language specialist from the DoD. We asked about the current tools that they use, their typical analysis workflows, and features that are missing. This figure shows the framework of Confides. In the back end, we use AWS Transcribe for automatic transcription. The user can upload audio files that are needed to be transcribed. The uploaded audio is transcribed and sent back to the tool. Users can select which transcriptions to explore and analyze. Due to confidentiality, AWS does not release any information on how this confidence score is calculated. Therefore, we stress that the confidence score should not be treated as an absolute truth, but rather a metric that offers analysts a way to gauge the potential flaws within the transcription. Once an analyst chooses an audio file to explore, they are met with this interface, which primarily consists of 3 main views. The transcription view displays an automatic transcription of a singular audio file from AWS. Each line represents a segment of the audio spoken by a specific speaker. To promote transparency, we provide both a visual representation shown by the opacity of the underline and a textual representation, where under each word a tooltip shows the confidence score. In the confidence overview, each rectangle element corresponds to a segment in the transcript, where the width represents the audio length of the segment. These rectangle segments are sequentially ordered from left to right. Each segment's average confidence determines its corresponding rectangle's opacity. This opacity value is calculated by averaging the confidence score associated with every word within the segment. Unlike the other 2 views, the word tree view will only be populated when the analyst provides a specific keyword they are interested in exploring with the search bar. In this view, we visualize a node link diagram where the nodes are words, and links indicate a word co-occurrence within the same segment. The size of the words in this visualization is proportional to the number of occurrences of the word observed. To demonstrate the applicability of this system, we present a realistic use case scenario that forages for information about pandas from the Nixon White House tapes. To answer the first question of the task, when were the pandas expected to arrive in the United States? The analyst begins by searching for instances of pandas within the transcription. The analyst observes that the individual confidence in the term pandas in the first instance is quite low compared to the overall average confidence of this line segment. However, the terms pan and panther also appear in this segment. Considering that pan is a subword or substring of the desired search term and panther is phonetically similar to pandas, the analyst plays the source audio and confirms that pandas is indeed inaccurately labeled.
The only way they learn now is to watch other pandas mate, you see. And so they're keeping them there a little while, these are younger ones, to sort of learn, how it's done. Now, if they don't learn it, they get over here, nothing will happen. So I just thought you should have your best reporter out there to see whether these pandas have learned. So now that I've given you the story of pandas, let you get back to your more serious question.
The analyst edits the transcription to reflect the source audio. While updating the transcription, the analyst discovers that line 709 refers to PANS and April 1st, with the latter two instances and a confidence score of 100% for both. The analyst decided the source audio was unnecessary as this line segment showed the pandas arriving in the United States with high confidence on April 1st. The analyst then moves on to answering the second question, which locations were considered for housing the pandas. The analyst searches for more instances of pan. Through this search, they observe that the word tree mentions National Zoo. The analyst continues flipping through the instances of pan. Line 704 catches the analyst's eye as it lists several cities, San Diego, St. Louis, New York, and Chicago, known for their zoos. The transcription shows high confidence for the listed cities. The analyst decides to cross-check the source audio due to grammatical errors in the transcription.
San Diego is limited to St. Louis, New York, Chicago, the rest. But this is the place for them from the standpoint versus international.
The analyst then looks up instances of zoo. With this search, they are able to confirm that despite considering the 4 listed cities, the pandas will be kept at the National Zoo in Washington, D.C., as one speaker reasoned that it is a tradition that all animals gifted to the United States are home to this zoo. Future directions for this work includes conducting user studies to validate the system's ability to assist analysts. Additionally, we would like to explore and develop design guidelines for visual representations of machine confidence. This concludes the presentation portion of the talk. I want to take this time to thank my collaborators for their guidance and assistance in this project. I am open to take any questions.
Okay, thank you, Sunwoo. So we have a quick question. As you said, in the future you want to investigate how users evaluate this system. Have you any initialized results for this?
Unfortunately, I recently graduated, so that would probably be a task for my lab mates who have taken on the next part of this work. But yes, I believe that we are continuing to develop this application as well as trying to see how effective it would be in helping analysts in gathering information as well as textually editing the transcriptions for errors.
Okay, thank you, Dr. Hua. Okay, now let's move to next talk, which is from Jordan. And let me share my screen.
Hi, I'm Jordan Wirfs-Brock, and I'm presenting work with collaborators Reese Sorenson-Graff and Sandra Bay. We focus on annotations, which are the titles, labels, text, and other elements that direct our attention and help us make sense of data representations. And we do so in the context of sonifications, data you can listen to, and physicalizations, which is data you can touch. Now, in a typical design process, you might move through data wrangling, analysis, maybe you'll iteratively develop and refine some VIS concepts, and perhaps at the very end you might add in annotations that can help support some of the key insights you want to convey. And for visualizations, this is usually just fine. But for data sonifications and physicalizations, where best practices are still emerging, annotations have to do double duty. They don't just highlight key insights, they also have to teach audiences how to make sense of the data mappings. What do the sounds even mean, and how should you touch and interact? So having them be an afterthought in the design process often won't cut it. So we posed a design provocation. How might we design more creative, approachable data representations by inverting the typical design process so that it begins with annotations and treating annotations as an integrated, holistic part of data representations? We explored this question through a research through design process that included a literature review of data viz annotation practices, close analysis of sonification and physicalization examples to understand their annotative techniques, creating tools for data designers to more deliberately make annotations, culminating in a collaborative board game, which we tested in a user study. In the literature, we draw from Rahman et al., who did a qualitative content analysis of visualizations to develop a taxonomy and design space. And this taxonomy includes things like enclosures, connectors, and marks. They also note that it's very common to combine annotative techniques into ensembles. Note that we were working from a preprint, and their work has now been published here at VIS 24, so go check it out. We then closely examined roughly 10 different sonification and physicalization examples, labeling their annotative techniques using that taxonomy, as well as new techniques that were not covered in the Rahman taxonomy. So here's an example of that analysis for a radio sonification in the form of an annotated transcript. Many techniques are somewhat analogous to those used in visualizations, but there are also some new ones, like the use of repetition, right? Audio elements on a loop to establish familiarity before a change. We synthesized these findings to extend Rahman's taxonomy to include how these annotative techniques might be specifically used in sonification and physicalization design. For example, geometric annotations, which are when you present a new perspective of a subset of the data, often occur as zoomed-in callout boxes in visualizations. But in sonifications, they might be an excerpted clip, perhaps surrounded by an explanatory narration. So here's a brief example from Neil Rizal for the BBC.
This is the sound of the pound against the dollar. Each chime is a passing day.
Or in a physicalization, you might change the viewer's perspective, perhaps by prompting them to shift their physical position or by presenting different images of the object. Based on our analysis, we developed 2 decks of cards, an annotation techniques deck that included both annotative forms, such as connectors, purposes of the annotations, such as adding context, and a second deck on the stakeholders who might be using physicalizations or sonifications, including roles like student or parent and goals like learning or entertainment. We developed these decks into a collaborative board game that encourages designers to create annotations for sonifications and physicalizations. It includes a game board and a series of worksheets for players to sketch their ideas, and you can find the full game materials and instructions in our supplementary materials. We ran a user study in the form of a 2-hour co-design workshop with 13 undergraduate students. They had been taking a data visualization class, so had been already practicing sonification and physicalization design, although were still beginners. We asked each participant to bring a sonification or physicalization that they'd been working on that they wanted to redesign. The workshop started with a group discussion about what annotations are and what purposes that they serve. Then participants played the annotation game in groups of 2 or 3. To play, each person drew stakeholder identities, and then using the annotation deck, they sketched annotations for their sonification and physicalization that could meet the needs of their partner's stakeholder identity. Finally, they swapped annotation sketches and evaluated their partner's ideas from the perspective of their own stakeholder identity. We collected a rich set of qualitative data, which we analyzed inductively using an affinity diagramming technique. Here are some examples of the annotation sketches. On the left, one participant redesigned a box whose weight corresponded to the carbon footprint of different kinds of food. By opening up the box, they could reveal more information inside. On the right, another participant reimagined a sonification of cat meow sounds and the behaviors they represent in the form of a pop song, where the lyrics convey how to interpret the sounds. So here are some of our key findings. Annotations for sonifications and physicalizations are hard. We don't have modality-specific design conventions to rely on. So designers often try to contextualize new experiences with more familiar ones. Putting annotation design in the context of a collaborative game helped participants think about the sense-making processes and needs of end users. The game was highly generative and fun. The ideas participants came up with weren't just for annotative elements, but for remaking the underlying sonifications and physicalizations, which illustrates how annotations are an integrated part of data representations. As one participant said, annotations feel like a part of the physicalization or sonification, rather than just a helping guide. And further, annotations have many purposes beyond simply helping someone read. For example, they can foster social connection. As we continue this work, we're hoping to do a more comprehensive analysis of annotative techniques in the hundreds of examples that exist out there in the Sonification Archive and Physicalization Wiki. We'd really like to extend the game materials so that they include examples and can be adapted to flexible design contexts, which would offer us more opportunities to evaluate their impacts. And finally, we'd love to further explore data annotation as a social activity. Thank you, and I look forward to your questions.
Thank you, Jordan. And it's very creative workshop based on the cards. So here is a quick question. So in your observations of the design space of annotations, do you think metaphor-based annotation design can be one of the main design roles in such as in physicalization? Because you mentioned
So the
go.
question was about metaphor, the use of metaphor in annotation. And I think that is a very powerful tool. That wasn't a technique we included in our game deck, but I think in the future ones we might, because basically what we found was that without established conventions to build on, people were drawing from metaphors in their life or metaphors in visual data representations. And so, yeah, I think in future iterations, we might more explicitly encourage the use of metaphor, because that is something that people draw on.
Yeah, I think it would be very interesting research topic. Okay, thank you, Jordan. So we move to our, thank you. We move to our seventh talk, which is from Floria. So I will share my screen.
Welcome to my presentation of AI, a visualization tool for image datasets. My name is Florian, and this work was done together with Luca, Marco, and Professor Wattenhofer at the Distributed Computing Group at ETH Zurich. The goal of this work is to visualize large-scale datasets. Here on the left, we have some images, and the problem is that we have limited screen space, and we want to position these images on screen and visualize them to a user that can then browse the whole collection. In this case, we only have a few images, so it's quite easy to put them on screen. We can imagine that we have a large-scale dataset which contains much more images which are harder to visualize all at once. Now, first of all, how do we find positions for these images? So usual approaches include using a clip image encoder. This is a multimodal neural model that finds embeddings for images, and these embeddings maintain some semantic information. So this means that images that have something to do with each other, for example, they both depict landscapes, will have similar embeddings that are close to each other in this embedding space. Now this embedding space is 512 dimensional, which is quite large, and to find 2D positions for images, we further use a UMAP projection, which results in these points that represent the positions for images. So once we have these positions, we can position the images at their coordinates, and in this a bit bigger example, we can already see that we get a lot of overlap if we have more images, and that it will be hard to visualize all images at the same time on screen. These UMAP projections and clip embeddings have been used in previous work. What we try to do different here is to really focus on large-scale data sets and to answer this open question, how can we reduce the number of images on screen in such a way that we can still make sense of the embedding space and that a user can really explore the image data set and not get lost in it. Again, we have our image positions, which are blue dots in this example here, with our screen space that's marked by this black box, and we can position the images at these points, but again, we have a lot of overlap. So our approach includes a multi-layered visualization in which at every layer we select some images, some representative images that we show to the user, and once the user goes on to the next level, by zooming in, we will uncover more and more images. Based on these image positions that we got through the projected clip embeddings, we now have to decide which images we want to show the user at the same time, because we cannot show all of them. We first choose a maximum threshold of images. In this example, it will be 4. With this number, we run the k-means clustering algorithm to get 4 centers. For every center, we now choose the image that's closest to the centroid and choose to visualize it. Those are the red points in this example here. While the red points make up the first layer of the visualization, the blue points will be shown in later layers. To descend from one layer to the next, the user usually has to zoom in. And once the user zooms in, some of the red points will disappear from screen and make place for more images that can be visualized. Our algorithm uses the regular tiling to subdivide the space. So starting from this original tile, it will be subdivided into 4 more. And once the user zooms in to one of these tiles, we now want to be able to visualize more than just the red dot. We can observe that for all tiles, but the one on the bottom right, we already have 4 less images in all of them. So once we descend, we can just visualize all of them directly. Now for the bottom right tile, we want to recursively run our algorithm again, but this time with an adapted k-means clustering algorithm. So the red dot is an image that was shown in the layer before, and for navigation purposes and consistency, we also want to keep this image as a representative in the next layer, which means that it should also be shown again. To achieve this effect, we keep the centroid that we already have in this tile fixed, which also means that the image that's closest to it will be retained. So this time we only have to choose 3 more centers, and once we have those, we can again take the images that are closest to those and show them on screen. In this case, we only have 1 blue dot left that represents an image that is not shown on screen yet, but this will be done once the user zooms in even more. So now let's look at the interface design of AI. This is the start screen that the user is presented with in our web application. On the top left, we have a dataset selector where the user can switch the dataset that's shown on screen. Top right, we have an info button that reveals some information about the tool. On the bottom right, we have a small minimap that shows the embedding space so the user can get an idea for what the dataset looks like. And on the top, we have a search bar. This search bar facilitates further features that we talk about next, which is semantic search. As previously seen, we embed our images with the CLIP image encoder into some high-dimensional embeddings. Now, CLIP is a multimodal model that's trained with image-text pairs, and we can make use of the different encoders that CLIP offers and that are used to map text or images into the same shared embedding space. And this means that we can take either text or image queries, pass them through the right CLIP encoder, and then do a lookup in our dataset database where we have all the embeddings stored of the images in our dataset, and we can find the closest match to it. In this case, for example, we can search for something like a king and find the image of the king on the bottom right, or we can even search with images and find the closest image in the dataset. This is what the user interface looks like. When we search for something, in the bar on top of the screen will be presented with the image in the center and its closest neighbors on the bottom that can also be clicked to explore the dataset further. Another feature we provide are AI-generated captions. In this case, we use the lava model for every image to generate some captions. This is something we played around with, so the user can really explore different captioning models and see how well they perform. We have a working instance of AI running online that ships with several datasets at the link shown on screen. Let's go through it quickly. We have a text prompt in the middle that we can use for semantic search. We see the images on the first layer directly on screen, and we see images of the layers beneath it as kind of blurred out previews. Now we can zoom in to uncover them. We can click on images to find more information, like the AI-generated captions. We can find a minimap to see where we are in the embedding space. And of course, we can also drag the screen and zoom with the wheel. Now, this also ships with several datasets. We can see that, for example, for MList, the clustering already has a lot of semantic information and clusters everything by the number that it represents. But we also have other datasets like Celeb AHQ, which has faces of celebrities, where you can also see clear clusters. So now for very few technical details, we ship AI as an open source web-based framework, which can be found on GitHub at the link shown on the right. For the similarity search and the semantic search, we need a fast backend, in this case Wirfs, which provides a vector database with very fast lookup. For the AI captions, we use the lava model. So that was all from my side. Thank you for your attention, and I hope you have some interesting questions.
Thank you, Florian. So it's very, very wonderful and useful tool. I also played online myself a little bit. So here is a quick question. Do you think it's possible to extend your framework to other datasets, say like documents or high-dimensional dataset for visual exploration?
Yeah, so we have an easy interface to extend it to other image datasets, of course. So that's the main idea. But we also actually have some other work on extending this to audio datasets, for example. So for audio, there are similar kinds of embeddings. They're not called clip, they're called clap, but it's basically doing the same thing. They're multimodal text audio embeddings in that case. And we also have some prototypes for interfaces that work similar to this one. But of course, for audio, it's a bit harder to visualize because you kind of have to listen to it. But you still have these kind of clouds that you can navigate through and where you can then play some audio snippets.
Okay, thank you. Great. Brilliant. Thank you. So now let's come to our last talk, which is from Kwesi. So I will share my screen.
We have this. Hi, my name is Kwesi. I'm one of the co-authors and the presenter for Opening the Black Box of 3D Reconstruction Error Analysis with Vector. To provide a bit of context, 3D meshes are very important for rover missions and geologic research. These 3D meshes are generated from the rover and helicopter images that are downlinked at JPL, and then these images are stitched together to create that 3D mesh. This stitching process is what we call simultaneous localization and mapping, or it's commonly referred to as SLAM. SLAM is a very reiterative process. Here are a few of the outputs that scientists would have to parse through prior to using Vector. On the left, we have this baked-in image of these vectors overlaid on top of it, alongside these lines of text showing the SLAM tracking process. So Vector was really born out of answering this question of how can we make this process easier? And to answer that, we first need to understand how SLAM works. So SLAM is really about 3D mesh generation. And this 3D mesh is created from a series of points. And we can think of each point representing a single feature. This feature is derived from a set of images. And each image has a tie point associated with it. And you can associate these tie points together to create that feature, or a feature track. These points are triangulated in 3D space. That is part of the SLAM tracking process. And you have the 3D mesh, and then each point is projected back into each image. This delta between the reprojection and the original tie point is what we call a residual. Scientists want to minimize this residual as much as possible because the smaller the residual, the closer the 3D mesh will be to the source images. So the current process, you have a set of images, the algorithm will place these tie points, it will try to minimize the error, and you're left with this busy picture and these large text outputs. And scientists need to comb through this output to understand how they can minimize residuals. So how do they actually minimize residuals? There are a few ways. They can remove the tie points, they can remove the features, they can remove the images completely, or they can adjust the camera properties. So really, Vector provides a comprehensive view of the image's tie points, residuals, and the mesh, so that scientists can quickly discover and resolve errors. At a high level, a scientist should be able to jump into Vector, having run the SLAM tracking process, be able to identify areas that are contributing to large residuals, remove these tracks, these bad images, and then compare the pre and post removal and see if that improved the tracking process. And Vector accomplishes this by providing a set of views starting with a global overview of the scene and then allowing the user to be able to drill down to areas that they've identified as problematic. This starts off with the scene overview, where you have a 3D viewport that provides the spatial context of the camera frustums alongside the 3D mesh, as well as two residual charts that we'll see in the other views provides a bit of continuity for the user. And really, the scientist up until this point has been dealing with an image data set. And so for the first time, they can really see in a 3D viewport how this terrain is being reconstructed. And so this really provides a very easy way for the scientists to identify problematic areas, because oftentimes these problematic areas are driven by spatial constraints. From this view, you can also go into the images overview. We had mentioned previously that scientists might want to remove bad images completely. This is one way they can identify them, by getting an overview of all the images in the dataset alongside the residuals. And again, we have the continuity of the residual charts. From that view, you can select an individual image, and you're greeted with that image with the tie points overlaid on top of it. We saw this in the previous tooling, but now it's has interactions as well as context of all the tracks associated with it, and again, the residual charts. And so this is much more powerful than previously done before, because now you have all the context associated with that image and you can action on it, right? So you can select a track and delete it and then rerun the SLAM tracking process. From here, you can also select an individual track and you're greeted again with the 3D viewport alongside the residual charts. And this really allows you to see all the spatial information and where the errors are propagating from. So overall, Vector really provides a visual analytics tool to facilitate error analysis for stereo reconstruction. It helps describe error analysis in the context of robotic exploration, but really it can be brought into the 2D to 3D context relationship. And it also illustrates how visual encoding and interaction can address these terrain reconstruction problems. In conclusion, Vector is currently used at JPL for error analysis of stereo algorithms. It was born out of a need to visualize errors and reconstruction parameters. There is future work to improve the iterative process between SLAM and Vector, as well as improve and provide more validation metrics. Vector has been used on datasets with hundreds of images and thousands of tracks, but there are areas of JPL and outside of JPL of millions of images, and so that would need to be further explored. Finally, Vector is open source. It is designed to be modular and plugin based. It's not just for NASA. It can be used for other 2D, 3D context applications. So it is available on GitHub. That's all from me. Thank you.
Thank you, Kwesi. So it's very good demonstration of how visual analytics can help with the domain experts. I'm wondering, do you have collaborate with domain experts from the beginning of the software design until the implementation, or what is the collaboration mechanism between the designers and the domain experts? Okay, so am I clear? Is the question that clear? I'm asking how do you collaborate with domain experts to develop such a useful tool? Okay, maybe Kwesi is not here. Okay, so thank you, everyone. We have finished all of our wonderful talks, and thank you for contributing to this section. And okay, now, bye-bye, everyone. Bye-bye. Thank you.